The idea that best covers all of these things that we have to explain is the nebular theory. Now, although we call it the nebular theory, something I want to point out, when I first started teaching a long time ago, it was referred to as the nebular hypothesis. Now, again, if you remember way back to the beginning of the semester what a theory is in science, this suggests that there's actually evidence that this is the way that things are happening. In everyday language, we talk about a theory as just an idea. We have no evidence for it. But in science, if it is a theory, it can actually explain a lot of the things that are going on. And there's evidence supporting these ideas. So it is the nebular theory, in that there's a lot of things that actually support the idea. Now, the overall idea is that the solar system formed from a nebula. If you remember previously, we talked about nebulae as these giant clouds of gas and dust, which then begin to collapse. Now, these ideas were actually proposed by Kant and Laplace, some philosopher-mathematicians, over 200 years ago, and it is just recently that we're starting to get the evidence in support of all of these ideas. The overarching principles that we need to remember is that gravity is going to be acting on these clouds. All mass attracts all other mass. So we have an overall nebula, specifically a dark nebula where we have low pressure and high gravity. Within this, we'll have regions that are going to be able to collapse under their own gravity. Now, as these pockets within the overall nebula collapse, they're going to be shrinking. But because of conservation of angular momentum, as they shrink, they're going to begin to rotate faster and faster. Because they're going to be rotating quickly in one plane, the other direction, gravity is going to be able to keep pulling until it settles down into a disk. So the direction where it's rotating, that plane is going to stay puffed out because of the motion of the disk, and in the other direction, everything settles down. So we have this relatively broad but flat, narrow disk. Now, as the material is sweeping around, if it has a highly eccentric orbit, taking it from far out of the solar system into the inner solar system and back out, then it's going to have a large chance of collision. So, for example, with this blue dot, if it sweeps in close and then farther out, it has a much higher chance of actually hitting things than if it had a nice circular orbit. What this is going to do is it's going to lead to frequent collisions with these things with highly eccentric orbits, and after many collisions, everything is going to start moving in circles where they have the least chance of colliding. This is kind of like bumper cars. If you've ever experienced or been around bumper cars, after a while, they all start to move kind of in the same direction, just because they keep bumping into each other. And if you have one person going in a wildly different way, they're going to get hit way more frequently. And so eventually they all start moving in the same direction. Now, as the matter falls, because of gravity, it's going to pick up speed, and eventually it's going to crash onto the disk. As that happens, friction is going to convert the kinetic energy into thermal energy. This is going to heat up the disk. What this means is that the regions where the material fell the farthest are going to heat up the most. They'll have the most energy that gets converted into thermal energy. So the center of the disk is going to become much hotter. Then, as we move away, it's going to actually cool off. The central region that is the hottest and that has the most material is the protosun. This is the thing that's going to turn into the sun. The disk of material swirling around it is the protoplanetary disk. This is where all of the planets will eventually form. Now, what's really moved the nebular theory into being a theory and not just a hypothesis is the Hubble Space Telescope and other very advanced telescopes. We can look into these nebulae that are actually in the process of star formation, and as we do, we can see young stars that actually have circumstellar disks. These, what we referred to previously as protoplanetary disks. So we can actually see these things. In these two images, we're actually looking at two different systems. The one on the left is edge-on. What that means is it's like we're looking across the disk. Notice that we have blocked out the central star because that star is going to be so bright we wouldn't be able to see the rest of the disk. But notice that it is very, very broad, although it is also very thin. The one on the right is face-on, meaning we're looking down on top of the solar system. Again, we have blocked out the central star, but you can see how broad this disk actually is. Here is our first lecture quiz question. Why do all planets orbit in the same direction in roughly the same plane? A. It is a great cosmic coincidence. B. They all formed in the rotating protoplanetary disk. C. The Sun captured them from other stars in similar processes, causing similar motion. Go ahead and think about it, and we'll discuss in just a bit. Alright, so why do all planets orbit in the same direction in roughly the same plane? It's B. They all formed in the rotating protoplanetary disk. That planetary disk is going to be very, very narrow, although very broad. And as the planets form there, their orbits are going to be within that overall disk shape. And all of the material in the disk is going to be going in the same direction, which also explains why it is that all of the planets orbit around the Sun going in the same direction.